All right, ladies and gentlemen, this is going to be your AP Chemistry lecture for kinetics. This is the last lecture of our kinetics unit. It's lecture 5.7. We're going to discuss catalysts here today. Make sure that you go ahead and pause the video, read through your learning objectives so you can kind of frame what you're supposed to be paying attention to, the types of things that you're going to have to be able to do and recognize in this particular unit. And here we go. Okay, so first we're going to start off with what a catalyst is. Now I know when we went back and we did the Pukey the Pumpkin demonstration, we knew that potassium iodide was a catalyst, and so now we're going to figure out exactly what that meant. We knew it made the reaction go faster, but we didn't know exactly how or why or the theory behind it. So we're going to look at that. Now, normally what a catalyst does, it's going to increase the reaction rate, all right? So that's basic number one. It's going to increase the reaction rate, and then the question becomes how, right? It makes reactions occur faster, but how? And then what we see is that it could actually do it one of several ways. It can provide an alternate reaction mechanism, right? So in 5.6, we looked at our reaction mechanisms, and the slowest step was going to be our rate limiting step, and that was what our rate was going to be determined by. So if we provide a different reaction mechanism that gives us kind of a go-around that rate limiting step, then what we can do is we can have a faster reaction, right? If we remove the rate limiting step, we can have a faster reaction. The rate should be higher. Another way that it's going to perform this function of increasing the reaction rate is simply just by lowering the activation energy. So again, remember back when we were looking at temperature effects and other effects on reaction rate, we saw that this activation energy, this energy barrier, if you will, was essentially what was stopping a lot of our molecules from reaching that transition state and then actually becoming a product. So by lowering that activation energy, if we keep the same frequency factor, the frequency factor should give us an indication that, hey, if we lower the amount of energy that's necessary there, we should have more molecules approaching that transition state and actually entering into the transition state and then forming a product. And then another key thing, this is what's going to make a catalyst, is that we don't have it consumed in the reaction. It's a spectator. It's going to look like it's a reaction intermediate a lot of the times, but what's going to happen is it's going to be produced at the end of the reaction. So the exact way that it enters the reaction is the exact way it's spit out at the end of the reaction. So if you look at the overall reaction, you'll see it on reactant and product side, and that's what we call it, a spectator, right? So it's not consumed within the reaction. All right, so now what we're going to do is we're going to take a look at an energy diagram, and so I'm going to go ahead, let me get my black marker here. Go ahead and just draw a standard energy diagram where I've got reactants, I've got products, and then this area represents my energy of activation. So pretty standard. Up here, this is my transition state. So this is my transition state up here. It's where the molecules start to transition and hybridize from my reactants to my products. So this is something that we've seen before. And so now let's look and see what this reaction would look like in the presence of a catalyst, because that's what we're really going to start with. And we're going to start with the same amount of energy for my reactants. But what we'll see is, hey, maybe it just doesn't take as much energy to get up over to that transition state. And so notice my transition state's here now. I'm just going to put TS. And my energy of activation is now dramatically reduced, right? And so the frequency factor, if I've got molecules that are actually approaching this activation energy barrier here, notice that a lot of them now are going to be able to get over that transition state. So that's one way that it does it. The other way is that we can actually see it, and let me see if it'll let me delete some of this stuff out. I'm going to delete all that. So another way that we can see it happen, and I want you to redraw this, is that I've got my reaction. Again, it's reactants and products. I've got my activation energy barrier here, my transition state. I'm just going to write TS. So that's my transition state. Another way that this can function is it actually can give me an alternative reaction mechanism, right? An alternative pathway to getting to a product. And you'll need to be familiar with these as well. And so what can happen is we'll see, right, we come up, we have that, and then we can end up with multiple humps here. And each hump represents a transition state. And so what we see is that within this, right, I've got elementary step 1, elementary step 2, and then my products are formed. And so you have to understand, like, this is elementary step 1, and then the other guy over here, this is elementary step 2. And so we can see that it'll give us another reaction pathway, because maybe going this direction requires too much energy, but we need some help to get through this way. Either the orientation factor is different or whatever prohibits it from going through the first way. The catalyst is going to actually help us go through this reaction pathway. All right, so just a couple of different ways that a catalyst can actually catalyze, but the big factor is that this energy of activation is going to be reduced. It's either going to do it overall, or it's going to provide us alternate pathways for reaction mechanisms here to accomplish this fact. Now notice another thing here too, and this is something I want to point out while this is on the board here. Notice now I have 2 transition states for my reaction mechanism, and this is pretty common. Just be familiar, the curve is still labeled the same. I've got 2 activation energy barriers here, and they can be the same, they can be different, whatever it is, but you should be able to label this. And if you don't understand, I know I'm not explaining everything here, the book does a really good job of explaining these multiple pathways. I think I don't remember what page it's on, somewhere in chapter 13 in your book, so you can look in there and find that if you don't understand or kind of get the general concept here. Okay? All right, so there's 2 types of catalyst. I'm going to go ahead and pause this. I'm going to type some stuff here on the old slide here. Well, I guess let me go ahead and explain homogeneous catalyst. A homogeneous catalyst exists in the same state. As my reaction. And so for this, like say all my reactants are gases, right? That means that my catalyst would have to be in the gas phase. If all my reactants were solids, my catalyst would be in the solid phase. If all my reactants were aqueous, then my catalyst would be in the aqueous phase. What homogeneous means is it's just going to be in the same state of matter as my reactants. And so normally there is some direct interaction, either through collisions, it's helping orient the molecules correctly, or it's transferring some energy to the molecules, whatever it may be, but that's how that particular catalyst works. And now I'm going to go ahead and pause the video, and I'm going to type some stuff down here for heterogeneous catalyst. All right, so here's our 4 steps for heterogeneous catalyst. And the first step is essentially we need to understand that a heterogeneous catalyst exists in a different phase. Or different state of matter. So these are going to exist in different states. So, for example, if my reaction was in the gaseous state, all my reactants were in the gas state, then my catalyst would be a solid. Or if all my reactants were in aqueous, it would be a solid. Or if all my reactants were solid, my catalyst would be a gas, right? So whatever it is, the state of matter is different for these. And so here's the 4 basic steps that we've got for a heterogeneous catalyst. And this is really talking about if my catalyst is in the solid state and everything else is either in a liquid or a gas state, all right, which is the basic or the most used or most seen use of a heterogeneous catalyst. So the first one is adsorption. Adsorption is when whatever the molecules are, is they essentially get stuck to the outside of your catalyst. They're not absorbed, so it's different from adsorbed is different from absorbed, right? When we think of absorbed, the molecules actually enter and go all into the center. Adsorption is when they only exist on the outside of the surface. And so the molecules are absorbed there, and essentially what happens is this adsorption orients the molecules in such a way that allows the reaction to take place, all right? So this is definitely the orientation factor. Heterogeneous is happening or helping with the collision theory and all this other stuff that we've learned about. The next thing is diffusion. So these molecules are stuck to the outside of the catalyst, and they're free to kind of move around and slide around on the surface, but they don't enter into the center of the catalyst. And so they're floating around on the outside, they're absorbed to it, and then essentially they're oriented in the correct way. And so when they run into each other, they bump into each other, collide, we actually get reactants formed. Or I'm sorry, we get a reaction and we get products formed. And so, and notice I'm not writing anything here, guys. So y'all are going to have to write down, absorption is when they get stuck to the outside of the surface. Diffusion is when they're moving around on the outside of the surface, but they're oriented in the correct manner. The reaction is when the reaction they collide and the reaction takes place. And then once the reaction takes place, whatever attracted them to this catalyst to be adsorbed is no longer there, right? The molecules have changed, they've reacted to form a product, and so once the reaction occurs, the molecules are actually released back into whatever state of matter that's relative to the reaction. All right? And with a heterogeneous catalyst, these are the 4 basic steps that it always follows. You're going to have to be familiar with these. The energy diagram, it doesn't matter if it's homogeneous or heterogeneous. The energy diagram is still affected the same way. That energy activation barrier is still lowered. I could have multiple reaction mechanisms that can take place now. Those kinds of things still exist. The only reason we're differentiating between the 2 types as homogeneous, heterogeneous is just so that you understand that there's 2 different ways to go about this, essentially. All right, and then the last one, I'm not going to spend a whole lot of time here because I know y'all did this in biology, but our enzymes, our biological catalysts are known as enzymes, and I've got 2 substrates or 2 reactants in this particular case. I've got my reactants here. They're going to move into the enzyme, right? This is my enzyme here. So my reactants will enter, and then the enzyme actually orients them in the correct fashion, gives them enough activation energy or overcomes the activation energy barrier to form the products. So these are the 3 things you're going to have to know. You can look them up in the book. I'm not going to spend the time since I'm trying to make this video a little bit shorter. But essentially, enzyme, substrate, active site. This is where the substrates are actually going to bind. And then once they react, they're released. And then they're ready to accept more substrate. Okay? Pretty basic theoretical stuff here on catalysts. There's not really any calculations that you're going to have to do. The big thing is being able to draw the energy diagrams before catalyst and after catalyst, and then just understand theoretically, hey, this is what a catalyst does. Okay? All right. Any questions, we post on Edmodo, or we'll see you in class.